Hello viewers, welcome back to the course on scientific computing using MATLAB. So now we will continue with the numerical differentiation as we have discussed in the previous lecture about the first order derivative. So today we will continue from that. So this is lecture 53. So in the previous lecture we have discussed forward operator, backward operator and the central operator. So let's take example that how we can use this one. Now suppose I have the data. Suppose I have some value of t and the value of u at t. So this value is given to me. Let it is 0, 0 0.25, 0 0.50, 1.25 and 1.50. So this is suppose my T0, T1, T2, T3, T4, T5 and T6. So the points value the function is given to me. So that is it is 1, 0 0.784, 0 0.649, 0 0.617, 0 0.718, 0 0.990 and 1.482. So this is value given to me, and this is suppose this is my u0, u1, u2, u3, u4, u5 and u6. So seven nodal values are given. Now suppose I want to apply the forward operator. So forward operator, I know that I want to find what is my u, the derivative I want to find what is my u dash at ti's. So this is I want to find using forward. So I know that for the forward u dash at ti, it will be u at ti plus h minus u at ti divided by h. So it is a equispaced data. So my h is 0.25. So I am finding my ti at this one, so I have to go one step forward. So in this case I will get the value here. So from here I can say that the u dash at t0, this one I want to find. So this will be u1 minus u0 divided by h. So if I solve this one, let's find out the value. So this will be 0.784 minus 1 divided by h is 0.25. Similarly, I can define the next one. So this is my u dash as t0, then u dash at t1, u dash at t2, u dash at t3, t5. So I can go up to t5 only because I am using the values after that. So if I want to find out the derivative at ut6, that I cannot do with the help of this forward operator. So this one I can find out. So if I solve this one, this will be minus 0.216. Similarly, I can solve the next one. This will come minus 0.135. Then next is minus 0.032. The next is 0.101, 0.272 and 0.49. So this is my this value. Now the same thing I can define the u dash at Ti using backward. So if I use the backward, then I know that I will apply this formula. So for the backward it will be, I will start from u dash T1, because u dash T1 means I am taking T1 minus and going back by h, u at T1, u at T naught by h. So that is the backward. So in this case I can go up to this. So this will be u dash at T6 will be u at T6 minus u at T5 divided by h. So now from here, whatever the value I am taking, so this will be same as this value. So this is the same as this value, and this last value will be same as this value. So u dash T5 will be same as u dash T6 when I take the backward. So total number of 6 values we can find using the first order derivative. The same way I can define for central. So this is u dash at Ti using central difference. So in the central difference I know that I was taking u dash at Ti, that is equal to u at Ti plus 1 minus u at Ti minus 1 u dash at Ti divided by 2h. So in this case I am going one step forward, one step backward, divided by 2h. So if I want to find this value, so I can take the value of u dash at T1. So this will be u2 minus u0 divided by 2h. Then I can take u dash T2. So it will be u3 minus u1 divided by 2h. So I can go up to u dash T5, because it will be equal to u6 minus u4 by 2h, and that's it. So in this case, when I was applying the forward method, then I was able to take the 6th derivative, the value of this function at 6 places, the derivative. With the backward also I have the 6 value, but using the central values we have only 5 values. So I don't know what is the value at u dash at T0 and u dash at T6. So whenever we have the data and we want to use our central difference operator to approximate the derivative, then we are able to find the value of the derivative only at the interior nodals. So these are the interior nodal values, T1, T2 up to T5. At the boundary values at this place and this place, we cannot approximate the value of the derivative using the central difference. So if I want to calculate the value of the derivative at the initial point and the last point, we may use the forward operator here, and in the end I can use the backward operator here. So that way we can approximate the derivative of the function for each value of the data point. So these all things will be used when we solve the differential equation. So in the solving the differential equation boundary value problem or the initial value problem, we have to take care that whether we want to apply the forward operator, backward operator or the central difference operator to approximate the derivative involved in the differential equation. So this is the use of how we can approximate, how you can use that different type of difference operator. Now, so this is we have done for the equispaced derivatives, equispaced data. Now I want to define the derivation with unequal interval. So in this case I have the x0, x1, x2 up to xn, y0, y1, y2 up to yn, and xi minus 1 is not constant. Okay, so in this case I can define my hi is equal to xi plus 1 minus xi, and this is a different. So we have the data that is not equispaced. Now suppose I want to use the derivative. So suppose my x0 is this, and I take x1 and I take x minus 1, this is my x2. Now my x0, suppose this is my h1 and this is my h2. Okay, so let us write my x1 can be written as x0 plus h1. My x2 can be written as x0 plus h1 plus h2. Now suppose I want to find the derivative of my function at this point with the help of, suppose I want to take the forward operator, so either using this one or this one. So let us write what is the Taylor expansion for x0 plus h1. This can be written as f at x0 plus h1 f dash x0 plus h1 square by 2 factorial f double dash x0 h1 cube by 3 factorial f triple dash x0 and so on. So this is the equation number 1, and I am expanding with the help of Taylor expansion, because I know the value of the function only at this point and this point. So that is why I am finding the value at x0 plus h1 with the help of Taylor expansion. So I can write here using Taylor's expansion. Now the same way I can define f at x0 plus h1 plus h2. So this one is again f x0 plus h1 plus h2 f dash x0 plus h1 plus h2 square by 2 factorial x0 cube by 3 factorial x0 and so on. So that I take as the equation number 2. Now from here if I want to find out the first order derivative. So the first order derivative, the simplest form is that using equation, so using equation 1 what I do, I take this on the left hand side, this is my value of f at x1, this is f x0, and this h1 I can take common. So from here I can write that f dash at x0 can be written as f at x1 minus f at x0 divided by h1, and then I will get the terms similarly minus h1 by 2 f second derivative xi, where xi I can take between x0 to x1. The same way we have done as for the equispaced data, and from here I can say that this is of order h1. So this is, I can say that in this case f dash x0 is approximately equal to fx1 minus fx0 divided by h1. And what is the h1? So this is h1 I can write as x1 minus x0. So that is my h1. Plus the other term is the order of h1. So that is my the forward operator for unequal data. So, this one we have defined. Now, similarly, I can define the higher order formula for first order derivative. So, first order derivative, you see that in this case I have used this one and I am able to get the derivative of the function at x naught with the order of accuracy with the order of h1. Now, I want to increase the order of accuracy. So, what I do, I want to find the higher order formula for the first order derivative. So, this I can write down. So, we can obtain from equation 1 and 2 by eliminating f double dash x naught. So, we can eliminate this one. How we can eliminate f double dash x naught? What I do that? So, I multiply this equation with h1 plus h2 square, because this is there, and I multiply this equation with h1 square, and then I subtract. So, I can write from here h1 multiply equation 1 minus h1 square multiply equation 2. So, this one we can do on applying now what I do, I will get from here h1 plus h2 square f at x naught plus h1. So, this is f x1 minus h1 square, this one I can take, and that is I can write f x2, because this is x2. This one I can write as h1 plus h2 square minus h1 square, and this one is equal to fx naught. Now, this one multiplied by h1 plus, so from here I can write h1 plus h2 square minus h1 square into h1 plus h2 f dash x naught. So, this one I can write from here. Now, this will be cancel out, because it will be h1 plus h2 square into h1 square, and this will be h1 plus h2 square h1 square divided 2. So, this will cancel out, and from here I can write the next term. So, the next term will be h1 cube into h1 plus h2 square minus h1 square h1 plus h2 cube. So, this is I can write divided by 3 factorial into f triple dash x naught. So, this is the corresponding to triple dash and so on. So, this one we can write down. Now, from here we are able to eliminate my second derivative f(x). Now, from here I can write, so this one I can be written as, so let us write this. So, this will be can be written as my h1 plus h2 square, this is my f1 I can write minus h1 square f2. Now I can take this expression on the left hand side. So this will be equal to h1 plus h2 whole square minus h1 square f0. And now I will get all this expression on the right hand side. So this is the terms we are going to get on the right hand side. I am taking this on the left. Now what I do is that if you solve this one, from here I can write this as h1 into h1 plus h2. So I can take h1 common and h1 plus h2 common. So I will get inside, I will get h1 plus h2 minus h1. So this will I get. And this will cancel out into f dash x naught, plus the same way I can take from here h1 square into h1 plus h2 square by 3 factorial, and inside I will get, so I have taken h1 square, so I will get h1, and this one minus I have taken h1 square, so that will go away. So it will be h1 plus h2, because only I will get h1 plus h2 into f triple dash x naught and so on. So this one I can write from here. So from here also this will cancel out. Now from this, now whatever the expression I get, I will divide this by this factor. So from here I can write that, I can write from here h1 plus h2 square f1 minus h1 square f2 minus h1 plus h2 square minus h1 square f naught. Now what I do, I divide it by this factor. So this will be h1, h2, h2 and h1, h1 plus h2. This one can be written as equal to f dash x naught plus, and from here also I will get, so that expression become, so this will cancel out. So it will be minus h2 into h1 square h1 plus h2 square by 3 factorial, and I am dividing by this one. So this will be h1 h2 h1 plus h2, and that will be x naught plus all other terms. So all the terms will divide by this factor. Now so from here, if you see that this will cancel out, so this factor will cancel over this one, h2 will cancel out, and this will cancel out with this h. So from here I can write directly that my f dash at x naught can be written as now h1 plus h2 square f1 minus h1 square f2 minus h1 plus h2 whole square minus h1 square f0 divided by h1 h2 into h1 plus h2. Now from here I will get the terms plus, so this will become h1 plus h2 into h1 by 3 factorial, that is 6, and then I can write these terms as xi, where xi belongs to x0 to x2. So this one I can take, because all other terms will contain the higher order of these terms, so that we can ignore, and this one. So from there, this is my expression for the the first order derivative that containing 3 points values, point value at f0, then f1 and at f2. So, this is of order h1 plus h2 into h1. Now, let us see. So, this is my equation number 3, because previous one has only 2 equations. So, I can have the value 3. Now, so this is of order this value. So, I can write that f dash x naught is of order h1 plus h2 h1 by 6, or 6 we can ignore. So, just this is of order, that is it. Now, let us take if h1 and h2 that is equal to h. What will happen if my data is equispaced? Then in that case what we will get? So, from equation number 3 we get f dash x naught. Now, this will be h1 plus h and h square. So, this will be h square f1 minus h square f2 minus, so this will be h and h 2h square. So, this is h 2h square. This is also 2h square minus h square f0 divided by, now here it is h, so it is 2h. So, I can write this as a 2h into h square, and the order becomes h2 h square. Now, I can take my terms common from here. So, I write my h square common. So, I can write from here, this will be 4 f1 minus f2, and this will be 4 h square minus h square. So, that will be 3 h square. So, this is minus 3 f0 divided by 2h cube. So, I will get this value because I have taken h square common, and this one I will cancel out. So, from here I will get that this is equal to 4 f1 minus f2 minus 3 f0 and divided by 2h. So, I will get this value for the first order derivative, and this is of order h square. So, in this case I am using the 2 values f1 and f2 to finding out this one. So, that expression becomes the very easy expression when the data is equispaced. Now, so in this case, now we will find out what about the, so that we will do in the next chapter. So, let me stop here. So, today we have discussed that how we can derive the first order derivative whenever we have the data which is not equispaced. So, in that case we get the expression using the Taylor's expansion, and then in the next lecture we will continue with how we can find the second order derivative. So, thanks for watching, thanks very much.